Okay, so we are talking about vertex form and transformations of quadratic equations. And if you remember back, we started talking a little bit about standard form when we talked about polynomials. But now we're talking about the graphs of quadratics. So we're looking at them as functions instead of just expressions. So the standard form for a quadratic equation would be y is equal to ax squared plus bx plus c, where a, b, and c are the um, numerical values that go in to that equation and change the look of the graph, and we'll explore all of that coming up. So we're starting with this parent function, which is y is equal to x squared right here. Okay, and what I want to do is I want to bounce back and forth through this video and use the calculator to help us understand and explore what some of these graphs are going to look like. So I don't know if you have any experience with the calculator, but we're going to type in to y equals, and this is how we graph. I think most of you have done this. So we're going to do y is equal to x squared. And the window that we want to look at is our normal standard window, which goes from -10 to 10 on the x and y axis. So if your window is anything different from this, you can always go to zoom and hit 6, and that zoom standard is will always take you back to that window. So we want to look at our graph. We hit graph, and we notice it is this U-shaped graph. Okay, and what that graph is called is a parabola. So we want to add that to our notes here. These are parabolas. Oops, sorry. Okay, and on the parabola, they are mirrored on each side, and they're split in half. And the thing that that is unique about them is that they can move all over the place. They can change the way they look, but they're always going to have a U shape. Now, the important thing that we need to understand is that each one of these has a vertex, which in this case would be the absolute bottom of this graph. So if you were to zoom really close in, the bottom of this graph right here would have an absolute lowest point, and that point is called our vertex. So if we're looking at, from a note-taking standpoint, we would have a point that would be very all the way down there, and that is called the vertex. Now, vertex, of course, is a point, so it has coordinates that would be able to locate it. Okay, so that starting from that is our parent function. So anytime we talk about x squared and the movement of this graph, we're starting from this point right here. Okay, so now if we want to explore this first part and we want to see what happens when I add 1 to x squared. So back in this calculator function, we're going to go back to y equals, and you can add in multiple graphs at once, so that's helpful when we're trying to explore things like this. So we're going to go y is equal to x squared plus 1. And let's just take a look at what happens to this graph when we graph it. So the entire graph shifted up 1 unit. Okay, so you can see it came from here, and then the vertex has moved up there. Okay, so the movement that occurred when we added 1 was that this graph, I'm going to zoom in a little bit, this graph was moved up 1 unit. So we can make a pretty good assumption that when I subtract 1, it's probably going to move down 1 unit. So let's go ahead and take a look at this. There we go. So let's just change this to minus so we don't have too many graphs going on at once. So there's our parent function again, and there is x squared minus 1. So we can see that the vertex has dropped 1 unit there. I want you to take note that everything else of the graph is the exact same. So basically we have just taken it and moved it down 1 unit. So we were correct that this did go down 1 unit. So I know you guys are thinking that, you know, the next thing we're going to look at is probably left to right movement. And you're correct. Let's take a look at this one where we're adding 2 to the x. Okay, so the difference up here was we were adding 1 or subtracting 1 from the x squared. Now we're adding this to the actual x value and then squaring. So let's take a look at this, and we're going to say, let's clear this out, and we're going to do parentheses x plus 2, close the parentheses, and square. So we changed it from 1 to 2 just to see a little bit more of movement. So if you notice, there's our parent, and it has shifted to the left 2 units. So now our vertex is here. From here, it moved over to the left 2 unit. So if you look at our graph, or excuse me, our equation, we added 2, and it moved it to the left. So that is opposite of what we typically think of when we think of the x-axis. We think of adding 2, we think of a movement to the right, but this ends up working opposite. So it is a minus, or excuse me, a left 2 units. So then, of course, this one is going to move the graph to the right 2 units when it's a minus 2. Okay, so what I want you to think about when you're looking at these graphs is I want you to think of it as if this is on a computer screen and I grab this graph with my mouse by the vertex here and I slid it up or down, left or right, the graph, the actual image of the graph is not going to change. It's going to just change location. So the positioning of the vertex is going to decide where this graph lies in the coordinate plane. So it can be, it doesn't have to be just right around here. It can be way over here to the right somewhere, or, you know, to the bottom left. It doesn't make any difference. These graphs move all over the coordinate plane, and it's all depending on where the vertex is. Okay, so the next thing I want to show you is what happens if I change and I make A negative. So everyone we looked at, A has been positive 1. We haven't changed that number whatsoever. So now we're going to make it to be negative. And let's take a look at what happens with this graph. So there's our parent function again. And what it did was it actually reflected the graph over the x-axis. So nothing has changed. This graph is exactly mirrored over the x-axis. And what made that change happen was we made this A value negative. So we're going to go back here and we're going to add that to our notes. Let's scroll up a little bit. And we're going to say if A is greater than 0, so it's positive value, then the graph is going to open up. If A is less than 0, the graph is going to open down. So you would have, for a positive A, your graph would look like that. For a negative A, your graph would look like that. Okay, so that's the basics of the movement. Now we're not going to be limited to 1 or 2 units. We can move whatever the equation tells us. So now let's take a look at why these things work and what vertex form is. So vertex form is y is equal to a times x minus h squared plus k, where h comma k is our coordinates of the vertex. Okay, so what I want you to notice here is this minus in the equation. And that minus is really just like an opposite. It's an easy way to think of it as an opposite, okay? So if my coordinates of the vertex were 3, 5, what that means is that I'm going to take my parent function, and something has moved this to where the vertex is located at 3, 5. Okay? So where people get confused is, why is this minus, and then we have a positive movement here. So the way to clear that up is to just think about the vertex being moved. Okay? So if the vertex has been moved 3 units to the right and up 5, then my vertex coordinates would be 3, 5. So if I were to plug that value into this equation, I'm just going to replace this h with a 3, and I'm going to replace this k with a 5. So notice that now this says minus 3 when my vertex coordinate for the x value is actually at positive 3.